For this video, we are going to solve for the Wronskian of the three different functions here. We have e to the power of x, e to the power of 2x, and e to the power of 3x. The Wronskian of a function is simply the determinant of an equivalent matrix involving these functions. This is an important concept integrated here because as we proceed later on to the process of the variation of parameters in solving higher order equations or higher order non-homogeneous equations, we are going to talk about the Wronskian. Now, the number of columns and rows will be determined by the number of functions here. Since we have 1, 2, 3 functions, our matrix for that we will be using to solve for a determinant, hence the Wronskian of the functions, is with 3 columns. Okay, so the columns will then be comprised of the functions themselves. And since we are solving for the determinant or the Wronskian of functions, we are expecting that we will have a 3 by 3 matrix starting with 3 columns here. What we just need to do is to look for the next few rows to be added here. Now, this could also be verified because the number of columns for solving Wronskian of functions will be determined by the number of the order of derivatives we're going to include together with the functions themselves. It's computed by n minus 1, where n talks about the number of functions. So 3 minus 1, we'll have 2. That would mean we will end up until the second order derivative of each of the functions. And looking into this, the first order derivative here and a second order derivative here, which ultimately checks our idea that we will have a 3 by 3 matrix. So let's talk about that. The first order derivative of e to the power of x is just e to the power of x, right, itself. The first order derivative of e to the power of 2x is itself, but it will be multiplied with the derivative of the exponent. So that's 2. This is also true with the third, e to the power of 3x, to be multiplied with 3 as a derivative of the, what do you call this one? The exponent of e to the power of 3x. In short, we could have this form here, which is not yet complete because we have yet to write our third row. But I'm just drawing it like this so that we could simplify the second row. It's just e to the power of x. And we need to simplify the second row because we will be using that for our third row. This is twice e to the power of 2x and thrice e to the power of 3x. So for the third row, which corresponds to the second order derivative of the function, so just simply derive the second row. So it's still e to the power of x here. For 2 to the power of 2 times e to the power of 2x, it's just itself, times again another 2 as the derivative of the exponent. And this is also true again with this last here times 3. So basically, we will have this final form of a 3 by 3 matrix following this, what do you call this one? These entries, e to the power of x, e to the power of 2x, e to the power of 3x. For a second row is e to the power of x. Look into this one here. Twice e to the power of 2x. And thrice e to the power of 3x. And then simplify the third row, still e to the power of x. You will have 4 e to the power of 2x and 9 e to the power of 3x. This is our matrix. And the determinant of this will correspond to the Wronskian of the 3 functions. So let me move here at the bottom because the Wronskian of e to the power of x, e to the power of 2x, and e to the power of 3x is the determinant, as mentioned, of this equivalent matrix. And how do we solve that? If we have a 2 by 2 matrix, similar to the previous videos, we have a specific formula, but we also did the diagonals there. Let's also copy that here. So we're going to multiply all diagonals from upper left upper right to bottom, upper left corner to the bottom right corner, which corresponds to this. Okay, multiply all this, but this is not just the first one because you also need to multiply this with this here, and since we have 3, it should go around to this one here, and this is also the last entry here will go around multiplying this too, but it looks a little bit complicated. So here is the suggestion for some, and I'm also going to suggest it. This one here, kindly try to reflect the entries. Again, it should not disturb the the matrix itself, but I'm just going to extend here or reflect the contents. So you will have e to the power of x, e to the power of x, e to the power of x, so that once we have our diagonal line here for the red one, so we don't need to do the curvature here. And then let me also add the second column, e to the power of 2x, twice e to the power of 2x, and 4 times e to the power of 2x. Don't need the last one because this is very needed as we look into this entry, that entry, and this entry here. So this red will be all positive, the products will be all positive, and then for the blue would be from bottom left to upper right would be negative. So similar thing as we go here and here, since we already have this value, so you will have that. And for our last, this entry here, that, and that here. So let's proceed with the red first so that you will not be confused with this process. Of course, you need to review as well your linear algebra for this. So for the first entry, you will have e to the power of x twice e to the power of 2x. This first diagonal, this one here, the first diagonal, times 9e to the power of 3x. That's for the first diagonal, plus the second diagonal with this one here. So e to the power of 2x times thrice e to the power of 3x. That's a 3. Let me do it again. Okay. Thrice e to the power of 3x times this one here, e to the power of x. Plus the last diagonal here. So you will have e to the power of x times e to the power of x times 4 to, e to the power of 2x. Okay, that's all for the red. Okay, now you can proceed now to the blue one before simplifying that, so that we will do it step by step. This diagonal here, or multiplying these entries. So these are also negative. So negative of the result for e to the power of x times twice e to the power of 2x times e to the power of 3x. Then also minus this entry here, this one, and that one. 4 e to the power of 2x times 3 e to the power of 3x times e to the power of x. And then minus, you'll have this here as well, this, that, and here. 9 e to the power of 3x times e to the power of x times e to the power of 2x. Okay, so simplifying all of them. Okay, let's have the first entry, e, and e, same basis. So 2 times 9 is 18. Your, what do you call this one? Your numerical coefficients. So 2 times 9 is 18. And then e to the power of x plus 2x plus 3x, that's 6x. Plus this second here. So you only have 3. That's for your numerical coefficient. E to the power of 2x plus 3x plus x is another 6x. Plus this one here, you have 4 e to the power of x, 2x, so you have 4x. Okay? That's for all the positive. Minus, you'll have here 2 times x, 2x minus 3x e to the power of 6x. Minus 12 e to the power of 2, 3, 1, so 6x. And minus 9 e to the power of 3, 1, 2, so you will have 6. Sorry, I am trying to review here the last. This is where I made my mistake, so pardon. I was confused why this is 4. So going back to this entry here, this is e to the power of 3x, by the way. This times e to the power of x and 4. Okay, this would mean, okay, changing this, I would know that that's incorrect because I cannot combine them into one expression, but nevertheless here, e to the power of 6x as well. So combining them, we have all e to the power of 6x, so we can combine the numerical coefficients. 18 plus 3 is 21, plus 4 is 25, minus 2 is 23, minus this one is 11, and minus 9. I believe you will get a result of 2e to the power of 6x. And this is the Wronskian of the three functions, which will be integrated if these functions will appear later on in solving non-homogeneous higher order equations using the variation of parameters. Thank you very much for watching.